All right, let's get started. First, as a reminder, today's lunch is a little shorter. So the afternoon session starts at 1:14, so 2 o'clock like today. The first stop, we have Gal Yona from Weizmann to tell us about decision making under miscalibration.
Okay, good. Can you hear me?
Yeah.
Okay, perfect. Okay, so first let me say that I'm very sorry that I can't be with you in person, but it's actually nice seeing and hearing some familiar faces and voices. Okay, so for those that I don't know, my name is Gal. I'm a student at the Weizmann Institute, and today I want to tell you about this kind of recent and somewhat ongoing work, decision-making under miscalibration. Okay, and this is joined with a guy who spoke before me. Okay, good. So, right, as kind of the background sentence that you've heard a million times, machine learning is used to inform consequential decisions about individuals. In this talk, I have binary decisions in mind, and specifically a setting in which I have a bunch of these binary decisions, and these are often not kind of optimized end-to-end. Right, think of a setting where I have multiple decisions that have significant overlap between them. So for this like really silly example, I want to show ads on Google. So maybe one binary decision is whether I show an ad on the right. Another binary decision is whether I show an ad on the left, right? Like there's a lot in common for these different decisions. Okay, so the setup that we're going to talk about and formalize is in some sense, I have one single model of the world, of ads, whatever, that then informs multiple downstream decisions. Okay, and I didn't mention, but please interrupt me with questions at any point or at the end if you prefer. Okay, good. So let's start by making this formal. I have an individual with features X living in some feature space RD. This is then transformed into a prediction. So for example, here I have P of X, which is in the interval 0, 1, maybe predicting some risk of heart attack in 10 years. And then I have a setting in mind where I then use this prediction to make different decisions. So for example, whether the individual would undergo some kind of diagnostic test is the first example, and maybe whether they would receive a certain treatment, etc. Okay, and these are binary decisions. So in some sense, this defines these two stages, the modeling part of the problem where I fit this, in this case, this risk prediction model, and then the decision-making part or kind of post-processing or transforming this estimate of risk into potentially actionable decisions. Okay, so I'll be focused more on this decision-making or post-processing part. Okay, so just to have this set up in mind, some of this notation came up also in Guy's talk. So I'm going to use P star to denote kind of the Bayes optimal predictor, or in this case, the true probability of some binary outcome Y conditioned on the features X. And let's, for now, just think of one of these binary problems, for example, whether to have the individual undergo some kind of screening test. Okay, and this raises kind of this simple problem of, given that I have a predictor P, which is some estimate of P star, how do I then use P to decide which individuals to screen? Okay, and actually when P, this predictor, is exactly P star, turns out that the answer to this question is both simple and very well understood. Basically, the optimal thing for me to do is to take the prediction of risk and basically decide kind of on the binary treatment if and only if this P of X exceeds a certain threshold, J star. Okay, so J star is going to be like a prime actor in this talk, so we'll revisit it again and again. And I want to make kind of 3 immediate comments about this J star. First of all, I'll sometimes refer to it as the therapeutic threshold. This was coined in this early work from 1975. The second thing is, as we'll see kind of later, this J star depends on the cost structure of the binary decision problem, in this case, this screening test. So think the relative costs of false positives as opposed to true positives, for example, right? So if you think about kind of thresholding at 0.9, right, essentially this conveys some sort of information, specifically that false positives are quite costly for you. So you want to be conservative. And finally, and this is actually an important remark, I stated this result as being true when P is exactly P star, but it's actually also true in that J star is the optimal threshold to use. It's also true when P is perfectly calibrated with respect to P star. Okay, so I don't have a formal definition here, but kind of think of it as if the data distribution is such that P star is the true conditional risk, then P kind of has a calibration error of exactly 0 with respect to this data distribution. Okay, good. So I'm storming ahead. So right after Guy's talk, the first thing that naturally comes to your mind is, okay, what happens when predictors are miscalibrated, as we know that they sometimes are, at least before you work very hard to calibrate them. Okay, so one kind of immediate observation that's simple but actually fundamental here is that when the predictor is not perfectly calibrated, right, it can even have some very mild but slight miscalibration, then actually still doing this strategy of thresholding at J star could be really kind of suboptimal or clearly not the thing that you would want to do. And I have here this intuitive example that I'll also revisit and make formal a bit later, but think of kind of a very simple setting where for the entire population, P star is at 1 minus alpha for some small alpha, and P, the prediction, is at 1. Okay, so obviously a toy example, this gives rise to exactly alpha miscalibration. And now consider a decision problem for which J star, this optimal threshold, is also very, very high. It's close to 1, specifically it's larger than 1 minus alpha. In particular, this means that false positives for this problem are very, very costly. Okay, so if you now think of taking P of X and thresholding at J star, right, it essentially treats everyone because everyone has a prediction of 1 and that's above the threshold. In particular, it means that as a binary classifier, the fraction of false positives that I'm going to have by the definition of P star is exactly alpha in expectation. And since this decision problem is such that false positives are very costly, then I'm going to experience very high loss here. Okay, so at least on an intuitive level, and I'm not really taking into account, or at least properly, this potential for alpha miscalibration, which could be very costly. So with this kind of intuitive example in mind, we think that this raises a very fundamental question, which is how do you translate potentially miscalibrated predictions into binary decisions? And I'll give like an overview of kind of our contributions here, and I'll go into a bit more depth in soon. But basically, we propose a new solution concept for how to go about this question. As I'll discuss, it's a distribution-free quantity, so like it doesn't depend on the underlying distribution. We refer to this as the regret minimizing threshold, J. And I've kind of emphasized here in this notation that it's a function of both J star, which is kind of the optimal threshold under alpha equals 0 or perfect calibration, and alpha, which is this kind of anticipated level of miscalibration. And we then proceed to actually give closed form expressions for how this regret minimizing threshold looks like. And kind of the spoiler here is that there are actually interesting cases where this is not exactly J star. So in some informal sense, you really should be taking into account errors in the way that you make predictions. Okay, so before I delve into these exciting details, I do want to give kind of a bird's eye view of where I see these types of questions and also how they relate to concepts in causality. So basically the starting point, I think for me, and partly why I'm excited about this line of kind of research is that, first of all, this distinction between modeling and decision-making, I think is very fundamental, right? It's not particular to this kind of setup that I've described here, where the model is an estimate of risk, right? It's, I think, equally valid or relevant when the model is a causal model, right? Like we use causal models to make decisions. And I also think that it's often the case that if I give you a perfect model, whether it's a causal model or a risk model, whatever, then it's actually quite clear how to make optimal decisions, right? Like the post-processing function, here I called it F star, it's often clear how to do it. But this raises this question of, okay, how bad can this composition of F star and my predictor P or my model P be when P is not guaranteed to be the perfect model? It's in some sense only my kind of best approximation of this perfect model, okay, taking into account both computational issues, sample complexity issues, things that we know that we are going to run into in practice. Okay, so I think this raises this fundamental question of when can we ever do better by making decisions differently? And then what do these different functions, F that are not F star, how do they look like? How do we go about choosing them? Okay, so this is like my pitch for why it's relevant for you and potentially interesting, even if you hate risk prediction models and everything that's to do with them. Okay, maybe questions at this point? Okay, good. Okay, so I'll make the setup a bit more formal so that we can actually go into some definitions. So this is everything that I've already said. We have a binary outcome Y and a feature space X. We have this P star, and we're then going to use estimates of this P star to inform decisions. And this result that I talked about before from this therapeutic threshold basically says that if you give me a binary decision that has some utilities given by U of false negatives, false positives, true positives, and true negatives, then if what you're interested in is kind of maximizing expected utility, then what you should do is you should take P star and you should threshold it at a J star that satisfies this equation that I have here. And it's a very simple derivation that I'm not showing. And I also want to mention, so I see that we have some like actual clinicians in the crowd, so maybe I need to be careful by what I'm saying, but I'll say it and you can correct me. But I think people are actually kind of involved in this exercise of coming up with these utilities and then deriving the optimal thresholds for kind of recommending treatment. Here I gave one numerical example that I found for colonoscopy, and actually in the paper, they go through the kind of details of how they came up with these numbers. Okay, so it's something that I think is really kind of done in practice a lot. Okay, so I want to talk about this concept of decision curve analysis. This was introduced by Vickers and Elkin in 2005. Basically, the way I like to think about it is kind of a simplified version of this full utility analysis that I talked about before, where you actually have to specify these 4 parameters. So basically, the starting point is this equation or relationship that we had before. Right, and now what we're doing is, let's call the numerator P and the denominator L. So you can also think of P as kind of the benefit from a true positive, in the sense that it's this difference in utility for making a positive as opposed to a negative prediction, conditioned on this population of people that actually have Y equals 1, the condition. And similarly, L is the harm from making a false positive prediction. So what they do is they say, okay, let's just fix one of these values at 1, say P at 1. And now we have this immediate relationship between the harm from false positive and this odds ratio of J star. Okay, and basically, if you look at this equation without kind of the details, but it immediately gives, right, it kind of says that I can think of the optimal threshold J star as also an equivalent parameterization of the decision problem itself, right, under these simplified utility assumptions. Okay, so specifically in the rest of the talk, whenever I want to index the binary decision that I'm actually talking about, I'll use J star to denote this. And the reason I'll do it is because of this relationship or equivalent view of the decision in the sense of the cost structure and J star as related in this equation. Okay, so I hope at least on a high level that's understood. So going back to this decision curve analysis, basically a fundamental question, right, like that a clinician, for example, would want to ask is, okay, you gave me a predictor, I want to use it for a binary decision problem J star. How good is it to use P for this problem? And the proposal in this line of work is to define this concept of net benefit. So specifically, it's kind of not a nice looking equation, but what's written here is actually very simple. The net benefit of using P for a decision problem J star is basically a weighted average of the true positives and the false positive predictions that you're going to make if you'll be using the binary classifier that's obtained by taking P and thresholding it at J star. Again, kind of specifically, this is with the weights of this combination given by P and L from the previous slide. Okay, so the way I like to think about this is, right, like the reason it's called a net benefit is in some sense it talks about, it quantifies the effective rate of true positives, effective in the sense of kind of discounting for the false positive predictions as they are valued in terms of true positives. Okay, so if this is the first time you've seen this, it might be a bit confusing. The details are not necessarily as crucial as much as you can just think of this as kind of a, if you're used to machine learning and loss functions, then think of this as some way to quantify how good are the loss of a predictors. Okay, so if you've believed me until now, then you might have like this other question in mind. So suppose I tell you that a predictor P has a net benefit of some value, say 0.1. Right, like what does this value mean? Is it high? Is it low? Right, like if you're a clinician, then does 0.1 justify actually using this predictor to make decisions? So the proposal here, which is kind of very simple, but it takes a step in this direction, is to define the clinical utility of a predictor with respect to a task as the net benefit after kind of discounting or removing the maximum between the net benefit of two other things you could do, which is to threshold P at either a value of 0 or a value of 1. Okay, basically these are kind of treating everyone or treating no one policies. And right, like the way you can think about it is these are things that I could have done, I could have implemented also if I didn't have the predictor at all. So in particular, doing worse than these strategies is like a huge red flag. So maybe like a simple sanity check, and if this quantity is positive, then it's like a measure of utility, basically. Okay, good. And I think one of the reasons why this approach has become really, really popular in this area of clinical decision making is that it lends itself to these very like simple and intuitive plots or graphs. So this is what a decision curve looks like. So here what we have on the x-axis is basically J star. So the different thresholds that represent, as I've mentioned, different decisions, binary decision problems. The y-axis is the net benefit. The solid line that's fixed at a value of 0 is the net benefit of the strategy of taking P and thresholding it at 1. So basically treating no one, and that's why it's constant at 0. The gray line that's kind of starting high and then decreasing monotonically is the net benefit of treating everyone. Again, the reason why it's decreasing is that as J star increases, the cost of making a false positive prediction increases. So this strategy becomes kind of worse and worse. And the other two lines, the remaining two lines, are basically just two specific models. So this is also giving you like a nice way to compare models. And something that should be very obvious, even for someone that doesn't know like anything about machine learning, is that you can really see from this graph exactly the range of thresholds for which kind of using this predictive model actually gives you clinical utility. Okay, so if you're a clinician and you're working on, I don't know, like a diagnostic test where you want to use it with a threshold of say 0.4, because that's a structure of the test, the utility is there, then you see that, okay, this model has clinical utility for this value. Okay, so that's just like a 3-minute, maybe more introduction to this area. Okay, so let's try to just wrap up this notation. I promise I don't have any additional these types of definitions. So in the beginning of the talk, I talked about these models, right? Like I made the distinction between models and decision making. So here, as I've mentioned, models are just predictions of risk. In terms of evaluating performance of models, the loss that I'm thinking about here is calibration error. The downstream tasks that I have in mind are basically all the different thresholds from 1 over m to m minus 1 over m. And here m is some parameter that's kind of controlling the granularity of these different tasks. Performance in terms of decisions, right, in terms of binary classifiers, is then measured using this negative of the clinical utility, as I've described. Decision making, or how I translate predictions into decisions, is by thresholding. So this defines kind of a class of different thresholds. And optimal decision making, which is, just to remind you, it's the decision making or the post-processing that I would apply to a perfect model, right? A model that has loss exactly 0. That's J star, or this therapeutic threshold. Okay, so hopefully, even if you miss some of the details, then this kind of high-level picture is fairly clear. Okay. Okay, you can definitely hear me, right? Okay. Okay. No, because you asked a lot of questions in Guy's talk. I'm not saying anything. Just wanted to make sure. Okay.
Questions also for your talk.
Okay, so I want to kind of just revisit this negative example that I gave in the beginning, right? So what do I mean by negative example? This is basically a case where I start out with a predictor that has fairly low loss, right? So it's not perfect, it doesn't have a loss of 0, but it has a low loss, some alpha that's actually quite close to 0. And then I want to reason about the loss of the binary classifier that's obtained by thresholding P at J star. And basically my point is that this can actually scale like alpha times m, where m is this granularity parameter from before. Okay, and specifically this like lower bound, with like ridiculously simple lower bound, is obtained by taking J star to be very, very close to 1, as I've had before. Okay, and you can go through the math of calculating the clinical utility here, right? The loss is just the negative of the clinical utility. basically the net benefit of the model and the net benefit of thresholding at 0. So these two quantities are essentially the same, right? They're the same because for when the predictions are 1 for everyone, then you're just treating everyone. So these things are the same, and just by substituting here the odds ratio, you get to a value that's exactly 1 minus alpha n. And the net benefit of treating no one is always 0. So here we have 1 minus alpha n. So the negative of this is alpha m minus 1, which can be very high when m is large. Okay, so this is the example from before. So what are the takeaways, right? The point is that naively using J star, even when the miscalibration is mild, could be bad. This also suggests kind of two natural things that you could do, right? You could try to make alpha smaller, right? You could do your best to really, really calibrate the model, right? But at the end of the day, some amount of miscalibration on the target distribution is unavoidable, just due to generalization. And also you could make M smaller, but then again, kind of the ability to make granular distinctions is usually something that you want to maintain. So this motivates kind of this shift in attention to a third knob, which is the mechanism by which we translate predictions to decisions. So specifically, we ask, given some value of alpha that's the anticipated miscalibration, and given a particular decision problem J star, which other threshold should we be using? Okay, and as I've mentioned, the kind of our proposal, which I think you can kind of say good things about, but there are also natural kind of extensions or other routes you could take, is to use what we call this regret minimizing threshold. Okay, so basically for every threshold, I'm defining a costs function, which is the maximal regret. Okay, and here I'll say what regret is in a second. The maximum is taking over kind of any possible target distribution and any possible predictor P, as long as the miscalibration of P with respect to this target distribution is at most alpha. Right, so I'm talking about a setting that is pretty worst case in the sense that I'm not willing to assume anything about the distribution that I would end up encountering, except that my predictor is at most alpha miscalibrated on. And then the regrets of using a threshold G with this predictor P is basically the net benefit obtained by thresholding P at this threshold J, minus kind of the net benefit of thresholding P at the best threshold, right? Like the best threshold in hindsight, right? And if you remember this notion of clinical utility, then you should see that this is like a generalization of it in the sense that for clinical utility, we competed in some sense only against two particular thresholds, 0 and 1, treat all and treat none. And here I'm saying, okay, I also want to kind of measure myself against every possible threshold, in particular the best one. Technically, this solves a lot of like annoying problems that come up when you want to use this notion of clinical utility directly. Okay, so this is at least at a high level, I think this is the concept of regret minimization that we work with. In principle, right, like it's a non-trivial kind of min-max optimization problem. The solution is not a priori clear. What we do in this work, and these are details that I won't go into, is we obtain closed form expressions for exactly how this threshold looks like when miscalibration is measured kind of using different popular notions. Specifically, we look at the maximum calibration error and the expected calibration error. And I've plotted here on the right kind of how J differs from J star. So you can see that in the middle, right, like for problems with an intermediate value of J star, then J is exactly J star. But when you move towards the edges, then J is in some sense a more conservative version of J star. Okay, so least the takeaway that I want you to have in mind at this point is that when we encounter decision problems that are kind of significantly asymmetric in that their optimal threshold is near the edges, then the optimal behavior, at least in the sense of regret minimization, is to kind of hedge your bets and take a conservative version of J star. Okay, so I think I'll take maybe 2 more minutes just to describe a bit of empirical validation of these theoretical results. So basically we look at 2 settings where kind of miscalibration is naturally occurring. The first is when we learn on small data. So as I've mentioned, even if we're calibrated on our small data, we expect to see some generalization error. And the second is kind of a setup of subgroup evaluation. So I'm evaluating on subgroups that the model was not actually trained on. This constitutes a form of distribution shift. So we also expect to see some miscalibration there. Okay, so specifically, just to give you like a touch of the results. So for the small data, intuitively, what I'm doing here is I'm training a model on small number of examples. So here increasing from 400 all the way to 1600. And I'm looking at the difference in clinical utility from using J star and using my proposed threshold, the regret minimizing threshold J. And here I've plotted kind of J with respect to different values of alpha, 0.05, 0.1, and 0.2. Okay, and what you should take away from this graph is basically that kind of when the number of training example is small, so we really, the predictor that you end up learning really is somewhat miscalibrated. So you should actually it's a good idea that you're hedging your bets and using this conservative threshold J. And indeed, there's an improvement in the clinical utility. Okay, but also expected is as the number of training examples increases, so in some sense, you're being overly conservative, right? Like you're losing clinical utility when there's actually no miscalibration. So then it becomes that using J, our proposed threshold, is actually worse than using J star. Okay, so this just speaks to the fact that, this is appropriate to the extent that you can correctly anticipate miscalibration. Okay, and the other setup is basically I'm taking one of the kind of features that are actually relevant to this task. I'm removing it completely during training time. I'm training a predictor, learning a predictor, and then I'm evaluating on the 2 subgroups that are formed by this binary feature. So everyone that has this binary feature set at 0 and everyone that has the binary feature set at 1. Okay, and this ends up creating some miscalibration, right? This is to be expected. And here are the decision curves the middle row is from using J star, and the bottom row is from using J, our regret minimizing threshold. Okay, and you can indeed see that like there is some miscalibration going on here in the low probabilities for one of the subgroups. This ends up being costly, actually creating clinical harm, right? In this area, we are worse than the baseline of treating no one, and the regret minimizing threshold kind of anticipates this concern and is conservative and says, okay, I'm just not going to treat anyone there. Okay, so this is just to give you a sense of the results, right? Like the takeaway is basically that we think that there are actually practical settings in which this can improve the clinical utility. Okay, good. So this brings me to my summary. So just repeating kind of things that I have already said. Basically, when predictions are used to inform decisions, which I think happens maybe more than we're actually taking into account when we're doing all this machine learning, then if you anticipate errors in the prediction, then it's actually the right thing to do in some formal sense. we go with this proposed solution concept of regret minimizing threshold. We show that there are actually interesting cases where it's not the usual threshold that you would use, and using it can actually improve clinical utility. In terms of like perspectives, thoughts, other things that I think you could think about in this context is, first of all, like other settings, right? Like I've described this clinical decision making, but I'm sure that there are other instances. Most notably, like other solution concepts, right? This is the thing I've presented here is very worst casey in its nature because of the fact that it's distribution free. Okay, I'm kind of coming up with a threshold that you should use that is the best threshold, irrespective of actually the predictor that you have at hand. So I think that's really like one very concrete question. It's also natural to think about stronger guarantees. For example, what about regret with respect to a richer class of threshold, maybe randomized thresholds? And finally, right, like at a very, very high level, right, like is there some general theory for optimal decision making, specifically in this regime of errors in my modeling stage and how to optimally take these into account? Okay, good. So that's it for today.
If the goal of a model, a prediction or causal model, is to make a binary decision, I'm curious about why you would approach that with this kind of two-stage, first fit the model, then make the decision framework, instead of just applying a loss function to the decision itself, which I think would be similar to like methods to learn optimal treatment rules in the causal world. And in particular, it seems very abstract level that would allow you to have the regret depend on the predictors instead of this worst case scenario where you've pre-processed, or sorry, where you fit a model, condensed everything down to a single dimension and are looking at regret on that.
Mm-hmm. Yeah, it's a good question. So I'm not saying this is the way to think about every possible binary decision, right? In particular, as I've mentioned in the beginning, there are a lot of cases where you kind of optimize, I called it end to end, right? Like you optimize directly for this binary target. I think my main point is, in many cases, we're not just talking about one binary problem in isolation, right? Like there's going to be the wonderful talk by Noah and Noam, I think later, right? Like if you're a big healthcare decision and you can a healthcare provider and you're faced with a lot of different predictions about individuals that you need to make, then there are clear kind of benefits from figuring out the shared component of these problems. So just even from a computational perspective. So I don't know, like from what I see, I think this is a natural thing that's actually occurring in a lot of cases, this distinction between modeling and decision making. I'm by no means saying that this is how you should think about every task, and this is like a very high level of abstraction that I think we should be thinking about, right? Like even algorithms that are designed to output predictions, right? Like part of my point is that we can't just forget about everything once I give you the prediction, right? Like it's not the end of the day.
So I'm curious if you thought at all about extending this to sort of an individual specific threshold. So if you can you sort of think about if you had, for instance, confidence intervals or some sort of sense for an individual, their miscalibration, can you use that to base your threshold off of?
Yeah, so I haven't thought about it yet. I think it's very natural once you start thinking about like these types of subgroup miscalibrations, right? Like different, maybe we anticipate different levels of miscalibration for different subgroups, for example, based on their fraction or mass in the population. And then we want to kind of be different in how conservative we are for different individuals. So yeah, it's a great point, but not one that I thought about.
If there's not a question in the chat.